Hello, everyone. Welcome to session 303, I guess. This is the session we talk about cloud-connected device on a global scale. It's the last days of reInvent. Enjoy the last session and go party after. So I will start off talking about a company called Banjo, which I am working with. And Brian from Panasonic is going to talk about a little bit more in-depth of technical information from how they scale the enterprise. All right, so start off by Banjo. So scaling from 0 to 6 million mobile users globally. All right, let me first start off by introducing Banjo, if you don't know it already. So Banjo is a real-time location-based information aggregator. Basically, we bring location and data together and show you in an app that works to the way that you can digest information by location. We're an engineering-focused company. We invest heavily on training and also getting resources for engineering. The app that we have done, basically it shows you all the events and recommends events for you and help you discover events and alert you when, in real time when there are events that matters to you. For example, concerts, sports events, and also like AWS reInvent conferences like this. We named the top developer and editor choice in Google Play, and we have been featured there a few times. We also named the top 10 world innovator in local by Fast Company. So let's talk about some growth factor, how big, how fast, and how wide do we grow. So we grew from 0 to 5+ million users in 2 years. There are users all around the globe, including Europe, Asia, and also United States. We indexed over 700 million social profiles worldwide, meaning Facebook profile, Twitter profile, Instagram profiles, and your favorite wines and everything. Processed over billions of location-based social posts since we started. So all these posts are indexable and searchable in real time. We geospatial indexed over 500K posts per hour. That's the number of posts coming in real time. And we also categorized thousands of events types that matter the most to all our users. And lastly, our backend is cranking hard to get the job done, so over 50 million background jobs processed daily. So let's talk about a little bit about our stack. We're a startup company. We have a very slim stack. So we start off basically saying, okay, Amazon is the good choice, so we put a lot of things running on Amazon EC2, Elastic Load Balancer is a friend. Basically, Amazon S3, Elastic Beanstalk, and we use Heroku as well to scale our services. We're Ruby House, Ruby on Rails, Mongo, Redis, Memcached. We use Sidekick for background jobs, as well as, lastly, the health monitoring and statistic monitoring with New Relics, PagerDuty, Papertrail, and Graphite. They are all essential to our company. So let's talk about how we start and how we scale to 16 million users. So first 6 months, we start from 0 to 1 million users, in 9 months actually. So we start off by just have a front end running on EC2, no background jobs, and hosted Mongo instances with a third-party provider, and we have no DevOps support. So the problem with that is we have limited engineering resources, no DevOps support, not too agile when we're deploying with like a script that you have to run a long time for deployment like Rubber. And we outgrew the MongoDB third-party providers limit, basically. So what do? So growing from 1 million, 2 million users, we start off by migrating our instances from single or two hosted EC2 to Heroku. Because we're running with limited resources, Heroku allows us to easily deploy and scale up and down. We also started having delayed jobs, meaning jobs running in background. For example, we start off by in-process background processing with Girls Friday is a gem in Ruby. And to queue, and later we migrate to Sidekick, which is a little bit more scalable. In-house MongoDB cluster, we brought in a lot of instances to support our growth in data, as well as our social graphs increased to 300 million plus profiles just within that time frame. So challenges, of course, we have explosion of social graph. We have a lot of data churning database, a lot of cost to process background jobs to render information to the users in real time, as well as latency. In order to pull information in real time, we have to process all those social feeds coming in to everywhere in the world globally. So from that, we also increased our user base to 4 million plus users. We started scaling the background jobs with Heroku. We have like 100 times the amount of workers that since we start when we have like 2 million users. That's a lot of resources to put in. Social graph also increased it to 400 million plus profiles. So most of the Facebook and Twitter profile who has been post publicly on the internet will have a copy of that. We also look at privacy very seriously. So most of the profiles that we have, we will keep track on the privacy settings. We index 1 month worth of global location-based posts, so we can search back everything within the month, and our front end will render the information to you in real time. We also process 10 million at that time, 10 million of background jobs daily, and still we only have one DevOps, and basically it's a support database as well. So the challenges, basically we are limited by Heroku's dyno. Memory limit is 512 at that time for the 1x configuration, and slower CPU because it's time shared by all the other processes running on the same EC2 host that they're running the processes on. So also, Heroku routing latency becomes obvious. If you have used Heroku, you know that there's a routing layer that route the incoming traffic through the routing layer to all the dynos that they have designed on EC2. So, and also, when we have 4 million users, our code base becomes rather large, and then we cannot have a very large concurrency processor running with limited memory and CPU. Well, at that time, 4 million users mean we have a lot more power users coming in to use our system, as well as consuming our resources. So we have a large increase of social graph due to the power users signing with millions and millions of followers from Twitter and Instagram. So now we have 6 million users. It's a good size, I think. 700 million profile index in our database. We switched from Heroku to Elastic Beanstalk partially on our backend for much easier scaling, managing memory, CPU utilization, availability zone, and all those goodies that comes with Elastic Beanstalk. We also switched from just using pure Heroku-based Unicorn process to Elastic Beanstalk with Nginx and Passenger combo. It's a 1-2 punch. We have 50 million background jobs running daily. Basically, we churn all the data from social media and render all the information to users in real time. And we have scaled to hundreds of EC2 instances with Mongo database, Redis, Memcache, as well as all the background jobs hosts to render the information for users before they come into the app. And yet, we still have the same DBA, same DevOps, one guy. So what are the pros and cons? Because why we switched from Heroku to AWS Elastic Beanstalk? So the pros for Heroku, to start with for a startup, is a very brainless deploy, very easy to manage by a simple command on command line or even on graphical interface. And also the rollback flow is very easy. You can just click somewhere or execute a command, and then your whole front end or back end will be back to the previous version. And the availability of dynos and workers are instantaneous. You don't have to spin up anything, wait for the machine to be available. They have everything available already. To set up the repro is pretty much a zero setup and maintenance. Of course, there's a cost to pay money to get that conveniency, but in terms of usage, it's pretty easy. And of course, there's no DevOps because they are the DevOps. Okay, the cons. So why is it that we move away from Heroku? They have limited memory and CPU make available for us to make concurrent jobs. The routing layer latency becomes obvious when we have like 6 million users with 700 million profile worldwide indexed. And there's no built-in auto-scaling provided by Heroku. We have to manually scale or use some external third-party provider to help us scale, auto-scale. And also the limited available zones, they only have Europe and US. And lastly, when there is issue on their platform on Heroku, we can't do much. We just have to wait until the DevOps figure everything out. At that time, they could have locked the API, and they would have limited your access to your application at that time. So we start looking at Elastic Beanstalk. Elastic Beanstalk is a service available by AWS. The pros, the choice of instance type, you can select as much memory, as large of instances or CPU as you want, and also increase the concurrency with the use of Passenger and Nginx, and the auto-scaling support comes to Elastic Beanstalk, make it easy for us to detect any spikes in the usage of a system, and we scale automatically. The latency of routing layer with Amazon is much superior to Heroku for sure, because Heroku is built on top of AWS as well. And the elastic load balancing helps us to make sure our resources are utilized on all the hosts in a fair manner. And also it's cost efficient. The cons, basically, in order to use this service, you have to learn a little bit about Elastic Beanstalk. In order to set it up, you need to set up a Beanstalk container and also the environment that fits your system and maybe your backend. The container updates are provided by Elastic Beanstalk is rather slow. They are currently with 1.9, Ruby 1.9, Passenger 3, and Nginx 1.23, which is a rather old version. And also, it takes time to spin up new instances when you're ready to deploy the next version of new code. It might take 15 minutes for us to plan and deploy accordingly, versus maybe Heroku, you can just deploy within 1 minute. And also, lastly, there's some learning curve in order to map your environment to Beanstalk. So you have to tweak a little bit of your scripts to work with the AWS nicely provided Ruby scripts and Bash scripts as well. So that's the caveat. So let's talk about how well it suits us. All the instances on EC2 are managed right now by easily. So we have one DBA and DevOps to help managing all our instances running Heroku, running MongoDB, not Heroku. Elastic Beanstalk will manage by engineering entirely, so server team will manage everything. Heroku services running on the background. We just keep it around because it's easy to scale and deploy. So the conclusion for us is Elastic Beanstalk and Heroku can be easily managed by small-sized, agile engineering team in a startup environment. So some recommendation for startups if you're in a startup. So start prototyping your product rapidly on a small-scale platform as a service provider that you can turn around your product and pivot very quickly. Make use of available add-on resources. Don't reinvent everything on your own, I think. It's major that you use available resources. They are cost-effective. They are just useful, like Papertrail, consume the logs for you, New Relics, hosted MongoDB to begin with, maybe Redis, Memcache, and metric system that suit your need. And last, also, you need to set up pager alerts. I know everybody will hate to get a page in the middle of the night, but make use of Scout app, ping them, and pager duty. They're awesome. They are just wake you up, but you'll be thankful for it. And make use of health and metrics dashboard. You probably need to set it up, but once you set it up, put it on a big screen TV inside your office. You will be glad that you find something right away on your TV rather than your customer is telling you. And lastly, deploy very frequently and scale up along the way and learn along the way, and your product will just strike. So, okay, now we'll do Q&A after Brian has finished the presentation, but I'm going to hand the mic over to Brian. He is remote.
Thank you, Justin. And let me echo his thanks to all of you for joining us on this last session. I think we've got, 45 minutes left so we're winding up. My name is Bryant-Eastham, and I work in corporate R&D at Panasonic. For my part of the session, we're going to discuss how to integrate small devices into the AWS Global Cloud. And in particular, we're going to talk about a technique for managing IP addresses. We're also going to discuss about how Puppet is part of this solution. So this presentation is a story of somewhat divergent paths. We're talking small devices on one hand, and we're talking global clouds on the other. Bringing these two together requires that we step somewhat onto the less traveled path, the path of resource-constrained devices. Now, when we're talking about cloud connected devices, we're talking from an assumption that these devices are small. And as we're going to see, AWS is going to add in the global cloud perspective. So let's talk about small. Small is a very relative term. Some people are going to think my cell phone is small. In addition, cloud is not a very well-defined term. So for our purposes, small means devices that have been extremely minimized for some purpose, and usually that purpose is to save money. We all love Moore's Law. It means that we get new laptops every year. But we forget that as soon as an embedded device is integrated into the infrastructure, Moore's Law becomes your enemy. That device immediately becomes obsolete, and at a pretty quick rate. So for small devices, we're going to talk about kilobytes, and we're going to talk about megahertz, where your typical phone now is gigahertz and gigabytes. When we talk about cloud systems, we're talking modern technologies. We're talking HTML, XML, SSL. These systems rarely take into consideration the effect that they have on very small embedded devices. And so we're going to try to reconcile these two. So besides just being small, device infrastructure has requirements that cause difficulties for cloud systems. The limited resources that these devices have mean that IT departments have a love-hate relationship. In some ways, they fear them, and that leads to some interesting consequences. One of them is whitelisting. So let me ask, how many people are familiar with the term whitelisting? Okay, so yeah, it still happens. IT departments can become very protective of these very small devices. Whitelisting also leads to these departments trying to get all of their communication going to the same set of very, very small, or small set of IP addresses. And that may include traffic that is not TCP-based. Not all protocols are TCP. So if you're going to try to do NTP and you've got a small device, well, that's a UDP traffic set. It's not going to go through your elastic load balancer. So let me go over some of the requirements for our cloud systems. We want to support whitelisting, and again, that means that I'm going to have a very restricted, very small set of IP addresses, and I want all of my traffic to go to them. I want to support UDP as well as TCP, and I don't want to pay a lot for a different load balancer. I still need to support auto-scaling, elastic load balancing, everything that AWS is going to give me to make my cloud global. But I also need off-instance logging and monitoring, so I can't bury these devices away. They need internet access. AWS is going to get us most of the way there, and what we're going to focus on now is getting that last 10%. So now that we understand some of our requirements, I'm going to present a solution that is based on EIPs, but before we get there, we need to take a detour into configuration. We're going to talk about a solution for that as well. So our goal is deceptively simple. We want to have a set of IP addresses, and we want those to be covered by a small set of instances. Those instances are going to provide whatever services we want on those IPs. And our methodology is to reuse as much as we can and invent only when it's necessary. Now, the benefit for us is that AWS has given us fantastic building blocks when we do have to invent. So the technique that we use is application-managed IP addresses. Standard EIP, in this case, is not enough. And there are a couple of reasons. First, we have this address pool. We need all of those addresses active all of the time. We just don't want them in reserve. We need them actually accepting traffic. We also are going to be scaling our instances, and that means that this set of IP addresses needs to move around. If our scale group is scaling up, then some of those addresses are going to have to move. If we scale down, they're going to have to move back to other instances that are still running. So by moving to an application-managed IP, we can take care of these problems. We can ensure that all of our addresses are active, and we can do that by monitoring. And we can use the EIP APIs to take care of our scale events. But this leads us to an interesting problem. Only VPC instances allow multiple EIP assignments. So that means that all of our instances have to be inside a VPC. So our solution requires multiple EIPs, and we want application control, which is going to, at some level, require some configuration. I mentioned that VPCs are required, and we also want our solution to use Puppet, and we want to leverage AWS. So keep in mind, AWS APIs always require internet access. Within a VPC, that means that you've got to have a bridge. You've got to have an internet gateway or some kind of bridge node. And that requires additional configuration. So now we've got a loop. We have configuration that requires having network access, but that requires configuration. So we've got a cycle. We need to break it. So an observation helps us to pick a solution here. We want to use Puppet, and we want to use VPC security groups as well to control access to this Puppet master. So this points to putting a Puppet master inside each one of our VPCs. Now, we know that we also require a bridge node in each one of our VPCs. So there's no reason to run two instances if one instance will do. And so we actually merge our VPC bridge and our Puppet master. Means all of our instances are going to initially be configured to talk to that bridge node. So here's our current configuration. We're going to use a VPC per availability zone that we want to deploy our solution in, and we're going to bridge the VPC by using our Puppet master. However, a global solution means lots of availability zones. That means lots of Puppet masters, and that's definitely not ideal. So what are we going to do with all these Puppet masters? Well, we know that we need multiple VPCs. It's not an option to put our entire solution in one VPC. We want a global, redundant solution. And we know that each one of these VPCs is essentially going to have the same networking requirements, the same configuration, and the same types of security groups. So they're really almost mirror images. We've solved one problem, we got our network access, but we've introduced another. And so what we need is a common configuration for all of our Puppet masters. This is where S3 can come in. S3 is a great choice here. It's global. It supports access control, and we can also share our S3 buckets among accounts. So what we did is implement a one-way synchronization from S3 to all of our distributed Puppet masters. In addition to synchronizing the Puppet information, for those who know about Puppet, we've got different scripts and files that we can deploy. We also centralized all of our RPM repositories. And so this synchronization from S3 to our Puppet masters also takes care of all of our RPMs. And this means that we can just upload a few files to S3 and do a global software distribution through Puppet. We can do all of our software updates within just a few minutes. So let's go back to where we started with our bridges, and we've got a performance problem now. Our solution leaves these VPC nodes all going through our Puppet master or our bridge. Well, we don't want all of our traffic to always go through the bridge. And we also haven't actually assigned any real IP addresses yet. We're just talking about configuration. So our solution doesn't stop here. All we do at this point is handle our node or instance configuration. Our configuration is going to include the information about the actual IP addresses that we want our application to manage. So, to summarize where we are now, we've got a configuration solution. It includes instance metadata. Now, instance metadata comes in two flavors. You've got instance metadata that's always available, your instance ID and your user data always available. You don't have to have internet connectivity for that. But we also have additional instance metadata. You're all familiar with your instant tags. Well, those, you need network access in order to get at those. We've got our Puppet configuration. We can have our configuration rules, and we can distribute files. And then we've got Amazon S3 access. So our little configuration detour is complete. We've got a solution now. We can configure all of our instances. And we're going to return to our EIP management solution. So our solution is going to require two host names. In this case, we're going to host both of these through Route 53. The first name is a master name. We're going to put every IP address that we want our solution to use into that name. We're going to configure a second address, which contains all of the addresses, but is also latency-based. So the first host name is used by our application internally. The second address is used by all of our devices. So when the device queries, it's going to get a regional specific address. Well, why don't we just use that for our configuration? Well, it is interesting, but a Route 53 latency query from within a region does not always give you the results for that region. It's a little strange, but it's true. So don't rely on using a Route 53 call from inside a region thinking that you're going to get that region's information. So in this case, each of our instances knows this master name, and we're going to use the EIP APIs to intersect that master list of addresses with the addresses that it knows apply to the region or the VPC that it's in. And then each of these instances is going to periodically check all of this information. So this is a 300-level course, so we get to talk about code, or at least pseudocode. So when one of our instances starts up, remember that it does not yet have a public address assigned to it, so it cannot communicate to the internet. So the first thing that it does is allocate an EIP. It will repeat trying to do this until it finally gets an address. Once it has the address, then it can communicate with the rest of the AWS infrastructure. Each instance is born with a single network interface and a set of private addresses. What we do is immediately allocate as many network interfaces as we can, and we populate all of the private IP addresses for each of those network interfaces. The number of addresses that you can support depends on the instance type. So it will try to fully populate all of its private information. Now, when it goes out and allocates these network interfaces, they may have public IP addresses already assigned to them. And so we notify the application right on startup the set of public addresses that it's been assigned. And that the application can then start whatever services it wants on those addresses. This is only the initial configuration. So what happens next is the periodic checks. So remember that it's not just you or your application that has access to this configuration. Unless you're protecting against it, any of your system administrators can launch it and remove one of your public IPs from an instance. And so the first thing that we do is we're going to use DNS and the EIP APIs and determine the current set of addresses for my region. That means I'm going to go to that global address, I'm going to grab those, and then I'm going to ask for all of the EIPs that are assigned in my region, in my VPC, and I'll intersect those. The next thing is I'm going to validate my public IP. If I've lost it, then I don't have any real API access anymore, and I need to reallocate my private IP. Now, if any of my addresses is no longer appropriate, maybe they've dropped some addresses from my master list, if I have those, I'm going to immediately release them. Now, I need to distribute the addresses fairly among all of my devices. So I'm going to look at the scale group that I'm in. I'm going to count up the number of active members in that scale group, and I'll divide that by the total number of addresses. Now remember, we want to over-cover our addresses, so I'm going to round up to get the number of addresses that I should have at any time. And then I'm going to release my addresses. If I've got too many, I will release them one at a time. If I've got too few, I'm going to allocate the total number that I should have. The reason that we do this is we want to minimize the amount of time that these addresses are not assigned. If I gave them all away all at once, then it will take longer for them to get reabsorbed by the rest of the instances. So I bleed them out slowly, but I allocate them quickly. And then finally, I'm going to look at all of the instances and see if any of them don't have a public IP. If any of them don't, then I'm going to release one. But I don't want all of my instances releasing one. And so I have to come up with an ordering. This is a very good chance to use instance IDs. We use instance IDs as our sort key, and the lowest one in the list is the one that's going to give up one of his addresses. We have to do that because that new instance is sitting trying to allocate his public IP, his primary public IP. In all of these cases, whenever we are going to release an address, we do it in concert with the application. So we will actually ask the application which address would be best for me to give up. Now, he may just return any of them, but he can look at, for example, the number of active connections on a particular server and give me back the address that has the lowest number. Then finally, we have shutdown. This is the orderly shutdown process. If the shutdown just occurs, somebody terminates the node, then eventually those EIPs that it was using will be released by AWS, and they'll be picked up by the other nodes. But if I'm going through an orderly shutdown, First, I'm going to release all of my network interfaces, everything except the one that I was born with. And that's going to release automatically all of the EIPs that are assigned to those interfaces. Next, I'm going to go through my primary interface. I'm going to release every IP except my primary one. I want to keep that last address because that's where my internet access is coming from, and I want to continue to be able to log and use AWS APIs during my shutdown process. And then finally, the instance itself is terminated, and AWS is going to release that last primary key. Okay, so this is the final view of our managed IP address solution. We start off with just user data, and we have our bridge, which is our puppet master. We have our configuration information in Route 53, that's our list of IPs. And we've got information in S3 and in instance data. So we've got our configuration and IP solution. Now we need to get back into having global scale. So lucky for us, all of the things that we have done with these instances play very nicely with AWS. First off, we can bootstrap our instances either through a custom AMI or by using Cloud Init. Auto-scaling groups, which are going to be part of any global redundant solution, are very good at setting user data and instance data. We can have our ELBs managed by our auto-scale groups. And then we're going to end up with two sets of addresses. First, we're going to have a latency-based Route 53 address for our standard TCP, HTTP. Those addresses are likely going to point to our ELBs, and they're going to have health check and everything else turned on. But I can't control the IP addresses of that set of ELBs. So I'm going to have another address. It's also latency-based, but this is pulling from a fixed set of addresses. That is my whitelist. Now, as soon as I have a public IP, then I've got internet access. I can remotely log. I can do everything that I want my node to do. I've got CloudWatch for monitoring. So let's play through this whole scenario. We start with our original goal. We wanted a set of instances, and we wanted a set of addresses. We're going to start these up inside of VPC, and we've got our puppet master, which is being used for our internet bridge. So next, we're going to handle all of our configuration. Our IP address set moves into Route 53, and we're going to add instance data and Amazon S3 for the rest of our configuration. Now, finally, we need to make this a cloud global solution. And so we're going to wrap each of these VPCs inside our auto-scale groups per region, and we're going to put our elastic load balancer back on the front. And with all of this, we've got CloudWatch that we can add for our monitoring. Justin mentioned PaperTrail. We use the same. We also use PagerDuty. I'll echo that. The 2 o'clock calls aren't great, but it's better than having your system down. And then finally, Route 53 with latency-based lookups. And so we've got our goal achieved. We've got a set of instances, a set of fixed IP addresses suitable for whitelisting, and we still have the global scale. So thank you very much. And I think that we are, looks like maybe 10 minutes for questions.